My name is Brittany Bruder, and I'm from the U.S. Army Corps of Engineers Research and Development Center Field Research Facility in Duck, North Carolina. And I'm happy today to talk to you about the Coastal Imaging Research Network, or CIRN, a grassroots organization where we use imagery to map coastal change. CIRN is a large organization with a lot of contributors from across the globe. However, I'd also like to highlight the work and contributions of my co-presenters, Dr. Katherine Brodie, who works with me at ERDIC, as well as Dr. Margaret or Meg Palmsten at the USGS. Today we're going to talk about quantitative coastal imaging. What is it, the benefits, and then we're going to talk about the formation of CIRN, the Coastal Imaging Research Network. And then CIRN is an organization that produces a lot of workshops and boot camps to try to further the transition and use of coastal imaging technology. And so we do that as well through developing and producing code that is open sourced, and we will chat about that code at the end. So again, first we'll actually start with quantitative coastal imaging. So what is coastal imaging? So we're really lucky in our field studying the nearshore that a lot of the physical processes and phenomenon that we're trying to observe has optical signatures, meaning that when we see a wave coming in from offshore, it starts to shoal as it gets in more shallow water. The wave becomes steeper and the face becomes darker, and we can actually see that. So we can see that physical process happening with our eyes. As the wave breaks, it produces white foam, and again we can see that, so we can tell where the wave is actually breaking and how long it is breaking. We can tell surface current similarly by looking at the white foam and seeing how it moves across the blue water, where we could tell the tide level, the changes in tide level due to the difference between the dark sand and the light sand. Same with extreme run-up is where we have the white bore of the wavefront coming up against the dark brown sand. So we can gather all this qualitative information, but how can we actually quantify what we can see? So we can look at this picture, and we could picture in other movies, and you could say that, well, the current, the foam is moving to the north at 5 pixels per second. Well, that's not really useful to an engineer or a scientist who needs to know the actual value of meters per second for a design calculation or something to input into a numerical model for validation. And so then we add the quantitative in front of coastal imagery. And to get this, we use a term called photogrammetry. And essentially that is just the mapping and providing of length scales to images to do our measurement in science. So the example right here is we have a picture from a unmanned aerial vehicle or a drone or UAV. It is looking out over the surf zone, and we can look at this picture and we can see our pier is about 2,000 pixels. Using photogrammetry and some calibration information of the camera and its position, we can make a map, kind of like Google Earth. And so we can actually see how long the pier is. It's about 400 meters, and not only that, we could provide an actual coordinate. We could give it a northing and an easting to say where it is in space. You can see we can pull some other information from that image, such as wavelength, wave direction, and so there's just a wealth of information. So this is an essentially new technology. Back since the 1910s, we've had aerial photography, cameras looking down that could produce relatively accurate maps that could be scaled. In the 1980s, started the work of Rob Holman at Oregon State University, where he investigated time average photography, where you average out a long time exposure, and that highlights areas such as average shoreline position and average sandbar position or wave breaking. And then later in the 1990s and the 2000s, Rob Holman with John Stanley developed this completely automated, robust network of digitized camera systems observing coastal sites around the world, and producing automated data products, so automated maps on the hour. One of their first sites was at Duck, North Carolina, shown in the bottom right. You can see the Argus Tower, and that has been in operation for over 30 years, providing over a 30-year record of our digital video record of our coast at Duck. Again, so Argus has really been the leader in coastal imagery. The tower has been in operation since the 80s. It has been a vast resource for engineers, scientists, academics to do research and to also develop their new algorithms. Since then, there's been automated shoreline position detection, bathymetry, conversions from imagery data, also wave characteristics, wave period, direction, surface currents. And so it's been a wealth of information to develop more technology. And through that and all the measurement resources at Duck, we've been able to validate this technology. And so it's a proven method to quantify nearshore processes over long temporal and spatial scales. So a quick example of this, of some of the data at Duck, we have our pictures, our normal kind of looking pictures of the beach, which we call obliques. And to the right, we have our georectified or our mapped version. So you can see here on the left-hand side, we have the sand. The right-hand side, we have the ocean. Blue, white is wave breaking. We actually had a nourishment project to the north of our property, so you can see the sand grow over time, and we could calculate beach area and how it's evolving in the life cycle of the project. We can actually also see different current formations and signatures in wave bar positions. And so it seems like a very beneficial tool. However, a lot of these things we can do already. It's traditional coastal monitoring efforts. We do surveys. There's also in situ instrumentation. However, the one problem with this is that although they are very highly accurate, they are expensive, they are time consuming, you have to operate in a harsh environment. It's a lot of resource intensive, and there's also safety issues. You can see the nearshore can be a violent place, particularly at points of interest such as storms. And they're also resolution limited, so in time and space, and we'll get into a little bit more of that in the next slide. To highlight an example, this is a map of an actual site that we had in New Smyrna Beach, Florida, where we had cameras installed. So when you would have a traditional coastal monitoring effort, let's say they were going to do a nearshore berm placement, they would install an in situ instrument. So you could see they installed 3 right here, and they can cover a certain amount of time. So you can see that we can cover that however long the battery life of those instruments are if you're not going to cable them. So we can collect over a long period of time. However, we only get those 3 points in space, so it's pretty limited. So to get more points in space, we could do something like a survey where you could grid the entire area of interest. However, again, those are usually resource limited, and a lot of times we can do that in the beginning of a nourishment and the end of a nourishment. But it's really expensive to do that throughout the entire period. And so because of this, we don't really get immediate responses to different storms. It's hard to isolate effects from the short-term and long-term seasonal trends. For quantitative coastal imaging, we get resolved in time and space. So this is actually one of our images that we've seen with this placement. You can see that they're placing sand off here in the offshore where it's blue and there's increased white. And so we can actually see how that bar is changing and the shoreline position. Depending on the data collection, we could even potentially estimate currents. And so we get all of this space measured as well as all of this point in time that's highlighted. So it's beneficial because we do have increased spatial resolution. We have hourly observations. There are some limitations, so it is less accurate than your in situ instruments. So we only have surface data. It's what we can see. So the idea is that it doesn't necessarily replace traditional monitoring, but it definitely can supplement it. And so the other benefit is that video technology is becoming even more accessible than ever. And so there's webcams, surf cams, phones, UAVs. So it's even becoming easier to employ. Okay, so what is the holdup if it's so easy? Well, there is a lot of photogrammetry and coding experience required. That's not necessarily taught in standard engineering curriculum. There are packages like in ArcGIS and things like that. However, they're very highly packaged and they're not really made for specific coastal needs and the requirements. And so the knowledge stayed in research settings, typically along academic lineages. A joke I frequently make is that all that kind of coding information literally stayed up in a ivory tower and duck in that tower. To the formation of CERN, the Coastal Imaging Research Network. And so this was a big lead by Rob Holman and Oregon State and other organizations to get more growth, visibility, and knowledge of coastal imaging. So more collaboration, shared resources, it's a bunch of government agencies, nonprofits, universities from over 21 countries. And we host an annual workshop and boot camp to foster collaboration and teach fundamentals every few years. This past boot camp was in Duck, North Carolina. However, we've had some in France and St. Petersburg. We're hoping to have the next one potentially in Australia. We had 75 attendees, 30% were international. We had 40 presentations. We have a lot of lectures, hand-on coding practicums, and demonstrations. So we had UAS demonstrations, installation of camera systems demonstrations, as well as just coding practicums. And we've had participants from across the world highlighted in the green. So the general boot camp overview. So we do go into theory, the photogrammetry fundamentals, and we do talk about secondary analysis. So, things you can get bathymetry, currents from using photogrammetry. However, the part that we really focus on is the actual processing or the mapping. So we feel like this is just a core tool that someone can use to further their own research or operational network. And so we kind of have a core code called the Introduction to Quantitative Coastal Imagery Toolbox. And that is kind of our main focus in the boot camp part of the CERN workshops and instruction. So this is just going to be a quick introduction to the code base. So the general organization is that these photogrammetry basics are kind of like baking ingredients. So we have a few staples that we use over and over. And if you use them in slightly different ways, you can get a lot of different tools. So, you have these basic tools or basic snippets of code, and then you can go make a cake out of them just like you would with milk and eggs. Or if you mix them a certain different way in different components, you can process UAV data. CERN toolbox, we had it more like a pre-made mix, and this would be more also like other commercial software. It makes it a lot easier to make. However, novice users are limited to a specific product. So if you buy cookie mix, you're going to get cookies. It's hard to revamp to make it into a cake mix. And it's hard to pull apart how actually the mix was made together. It's hard to learn make from scratch or repurpose. So a lot of the GUIs and more other commercial products have this issue, but are even more amplified. So there's additional features, and it simplifies the code greatly. And add more ingredients that you may not need. So we want to build a toolbox that highlights the fundamental concepts, but we can still use to make a product. So we want to kind of bridge the gap between theory and application. And that way users aren't just limited to cookies, they're not just limited to cakes, but they have the fundamental knowledge to bake. They know how to make their own coastal imaging processes and operational workflows in their own projects. The code itself is, we have a series of kind of ingredients or core functions, and then we have kind of a recipe card that goes through them and shows it in an example how they're used. So we have a linear set of example MATLAB functions. There is a Python version that has been developed. And so it calls upon these sub-functions that you could then go on to use to develop your own code. Right now it's focused on hovering UAS, UAVs, or multi-camera stations. We have demo data that the user can use. We also try to break up the code to save intermediate steps, so you don't have to restart the entire process if you end up wanting to change resolutions or change purpose of what you want your data to be. And we also have a lot of documentation to help explain coordinate systems and how we define our equations so that it could be translated into other vernacular. So it is found on GitHub, on the Coastal Imaging Research Network's GitHub, where we have a lot of different code. There's also a publication in SoftwareX. So these are just some example products of all that you can do with the code and example imagery. To the left, we see these are just some example UAV imagery that we've been able to run and use bathymetric inversion algorithms. So to get that initial mapping, we use the toolbox. And you can see here the bathymetry has been overlaid on the actual maps. So not only can we take imagery and map it, we can actually take measurements that we have and map them back onto imagery, which is also useful. It's almost like augmented reality, and the toolbox has some short tools to do that. And so these are just some points in space that have been projected back onto the image to see where they are in a more of a natural view that someone would see. This kind of aligns with something that has been developed by OSU, which is the idea of pixel instruments. So you can pick a point in space, particularly here, and if you pull the pixel intensities, you can see again with that dark light changing of the wave face, you get a wave signal. And here they have a show where a pressure sensor was placed right by the pixel instrument. And you can see they're very similar plots, and you can pull things like wave direction, wave period, wave celerity from just imagery. Another thing we can pull, again with these pixel instruments, are lines of data. So right here they took a line of pixels and they made something called a time stack, which is a frequent tool used and can be produced in the toolbox. And again, it is really good to see the extent of run-up, track it, the period, and it's just useful to estimate wave celerity. Again, these pixel instruments can be replicated multiple times, so you can have an array, and so you can see how this would be much, much cheaper than installing a ton of pressure sensors or along the coast in different transects, where you just have to install one particular camera system. We are, again, an open organization, so we welcome you to come join us. We have our GitHub, which is found at the first link. You can message us on LinkedIn to join different committees and the email list. There is going to be a 2024 boot camp, probably near the end of 2024. And workshop. There are going to be some seminars throughout the year, so please look at LinkedIn for updates, as well as the Coastal List, which is a Google group you can sign up for. We put a lot of announcements there. You can learn more at the publication that was done on the Coastal Imaging Research Network. However, we're just really excited for, again, to transition this technology and welcome many more participants. So with that, I'll let you go, and I'm happy to answer questions during the other workshop sessions. Thank you very much, and have a great day.